नहमदुहु व नुसल्ली अला रसूलिहिल करीम अम्मा बाद फ़अऊज़ु बिल्लाहि मिनश शैतानिर रजीम बिस्मिल्लाहिर रहमानिर रहीम रब्बी इश्रह ली सदरी व यस्सिर ली अमरी वहलुल उक़दतम मिन लिसानी यफ़क़हू क़ौली अल्लाहुम्मा अन्फ़अनी बिमा अल्लमतनी व अल्लिमनी मा यनफ़अनी व ज़िदनी इल्मा वल्हम्दुलिल्लाहि अला कुल्लि हाल व अऊज़ु बिल्लाहि मिन अज़ाबिन नार। Welcome to W340 Control Systems lecture. We have been studying chapter number 2, Mathematical Modeling of Control Systems. And there are some of the chapter breakdown. We are studying the third part of the chapter 2, that is Automatic Control System, and we have been discussing the block diagrams. And a block diagram is the like black box that gives the input-output relationship of a system. And we show a system in the terms of block diagram, and inside a block diagram we can, or sometimes it contains the name of the system, or sometimes a description of that system, and it's just like a black box. We are not giving so many details, and the block diagram can be further divided into sub-block diagrams. And sometimes the block diagram, if we have a mathematical model of the system that can give us the gain in Laplace domain or written inside that square box, and it can also show a mathematical symbol. Something, for example, there could be an integrator or a differentiator, and we can represent that block by an integration mathematical symbol or d by dt symbol for a derivative. And on the bottom of the screen we see a typical block diagram. There is input signal x of s, there is an output signal y of s. How is that obtained? By multiplying the input with the gain of the system that is given in Laplace domain. We are working in the Laplace domain. Then one other part of the block diagram, when we divide it into subsystems, it contains signals. As we saw in the previous diagram, x of s was a signal, y of s was a signal, and it has a square or a rectangle that represents a part of the system. And in a block diagram, we have a third component, that is a summing point. And a summing point shows a place where two or more signals are being added together. And in bottom screen you can see here in the figure on the left, we have a signal x and y coming to a junction. We say it's a summing point, and there is there is this is a positive sign. This one is a plus sign. I'm sorry, it's not clear. Here is a plus sign, and the output of a summing point is this summation of the two input signals x and y. Similarly, if I had a summing point that was taking the difference of the two signals, or saying x minus y, that is represented by showing y entering the junction with a negative sign. And there can be more than two inputs, there can be three inputs, there can be 4, 5, as many as are conveniently possible to draw on the paper. And in this diagram we see there are three inputs. Output is the summation of all three. Sometimes the summing point is represented with a circle with a cross, and the signal symbols are inscribed inside that circle. And as we are following the Ogata's book, Modern Control Engineering, it prefers the circle with the cross notation. And here is a particular block diagram of a generalized clock loop system. Here we see there is a reference signaler RFS, There is a plant GFS, the input of the plant is CFS, input to the plant is an error signal, taking the difference of the reference signal and the output signal. And at the summing point, we have renamed the output signal as BFS. We will shortly see why we did it. And then the error is the difference between our desired input reference and the sample of the output signal. And that error signal is being fed to the our system, the GFS. And there is also a branch point. A branch point is where we are taking a signal to another part of the block diagram. That block diagram is again, and here we name some signals. Here is the reference input signal shown by an error signal, EFS, then output signal, then there is a sensor. In the feedback loop, we sometimes or most of the time the sensor has its own transfer function and it's also a sub-block. It has some input-output relationship given by HFS, and the output of this sensor is BFS, that's known as feedback signal. Then we define some transfer functions that give us the ratio between two signals of a particular block diagram. One of the transfer function is open loop transfer function. That is the ratio of sensor output signal to the error signal. And you can see here, if I start a block diagram from EFS, taking that is my input and BFS is my output, and let's cut off this point here and ignore the output going elsewhere. So the relation between BFS and DFS is GS times HS, because the two blocks that come in series, their combined transfer function is the multiplication of the two. So these, for this entering point and this leaving point, these two are coming in series. So the transfer function is the product. Then is a feed forward transfer function, that is the ratio between the output and the error signal. So if you see that this was original plant without any control system or feedback control, so it is our the feed forward transfer function is the transfer function of our open loop system. Then is the closed loop transfer function, that is the output divided by input of this whole closed loop system, and the formula is we have derived it in our previous lecture. We will use that information here, that it would be the ratio of GFS divided by 1 plus GS times HS. What is GFS? GFS is the forward path gain, HFS is the feedback path gain. Then let's consider a real system defined by some integral differential equation. And for physical systems, we have defined mathematical models. For some of them, not all of them, for some of them we have pretty accurately defined mathematical relations. And we can describe a system with differential equations, different or integral differential equations. Obviously, integral can be changed into differential by taking a derivative of the whole equation. So let's consider the equation YFS, and this represents a signal that has three inputs: AFS, BFS, and CFS, and it has three gain blocks: G1S, G2S, and G3S, and this is how they are related to the output. So can we draw a block diagram for this equation? How would it look like? This here. This one. This is AFS is input signal, BFS is input signal, CFS is input signal. AFS is multiplied with gain G1S, B with G2S, C with G3S. And if 3 are summed at the summing point, this plus comes up plus here, Fs, this comes with a positive sign, this comes with a positive sign, this signal comes with a negative sign. So YFS would be this particular equation. Let's see another equation. This one is YFS, and here instead of G1S or G2S and G3S are given actual values. So output is 5 by S times Fs. So we have G1 of S is 5 by S. Then G2 of S is 11S. We multiply with BFS. And G3 is 12. This is an equation in Laplace domain. And obviously it has a corresponding differential equation. And for reference, we will recall our previous information. That is how would this equation look in the time domain. And if how the equation would reflect in the time domain. So y of t is 5 times integration of a of t. So a of t is the original signal whose Laplace transform was capital Fs. And we should see that Fs over S, that is an integrator plot. Then plus 11s BFS. This S means in time domain it would be replaced by a derivative. So 11 times derivative of b of t minus 12ct. So as the in Laplace domain is being multiplied with the constant is same as being multiplied in the time domain. So how is block diagram? Here it is 5 by s, 11s, 12. First signal is positive, second is positive, third one is with a negative sign. And we can also further divide these blocks into sub-blocks. How? Let's say 5 by s can be divided into these two or series blocks 5 and 1 by s. 11s can be subdivided into 11 and s, and 12 it was the only one. And this is the representation of we are representing the block diagram in S domain, or we're given the gain GFS. And it's also possible to describe the function of this block by the mathematical symbol. So 1 over S is the process of integration, and this is the process of differentiation. So the alternative way to show the same block diagram is this one. This is 1 over S is replaced with an integration sign, S is replaced with a derivative sign, and, and it's also we have EFT here. If I see in the time domain, it would be EFT, and this will be Y of t. Similarly for the other points as well. And here is an exercise. Take two equations, this one x2, and try to show it in the form of block diagram, and the other one too. And we have done it in classroom, and I hope you will be able to draw the two equations. So when we talk about the block diagrams, and we can add up subsystems to give us a bigger block diagram. In this figure, what we have two subblocks. Gain of the first block is G1S, the gain of second block is G2S. So is it possible to combine the two in a single block diagram? Yes, it is possible. This is the series connection, and the equivalent would be G1 times G2. And we have also a parallel connection, that is two blocks, and their outputs are being added together to give the output, and input is same to the both of the blocks. So this is known as a parallel connection. The output CFS would be G1 plus G2, and there is also a closed loop, and this one is the uh, closed loop connection. We see GFS and G2FS are the two blocks, and they are connected in a closed loop fashion. We are comparing the output of G2FS with the input, and that is being inputted to GFS. This is the closed loop connection. So these are the basic connections, and we will be making use of them when we go to block diagram reduction. In MATLAB, MATLAB gives us facility to calculate overall block diagram for two blocks connected either in series or in parallel or in loopback fashion, and how it would be done. If, for example, G1 of S is a Laplace transform of a block diagram, and obviously it would be a fraction and with some numerator polynomial in S and a denominator polynomial in S. For example, G1 of S is 10 over S squared plus 2S plus 10, and in MATLAB the polynomials are represented with vectors. Numerator is a constant 10, and so it's a vector of element having only just one element represented by your 10, and denominator is our polynomial of degree 2, and it is represented by this vector, and it has two elements 1, 2 and 10. Similarly, if I have a second block G2 of S, 5 over S plus 5, the corresponding vectors are 5 and 1, 5. And if I have connected them in series connection, then MATLAB gives us a function series, and it has 4 parameters, numerator and denominator for the two blocks, and the output is the numerator and denominator vectors for the series combination. In series combination, I will be multiplying these two, and after multiplication I would be getting this transfer function. Okay. 10 times 5 is 50. S square plus 2s plus 10 times s plus 5 is s cube plus 7s square plus 20s plus 50. And this block would give me two vectors, and numerator vector would have only 50, denominator vector would have 1, 7, 20, 50. And if I want to display in MATLAB in proper fashion, I mean in polynomial form, then the command is print sys num then just give it two vectors and it will display like a fractional polynomial. And similarly, if I have two blocks G1 and G2 connected in parallel, it will give the parallel transfer function, it will give the feedback the overall transfer function. Now, how do we draw the block diagram? We will study in detail in chapter 3, and there is a little example that is easier to understand. For if we have an RC circuit, and we will try to construct a block diagram for this particular circuit, and we have a resistor, a capacitor, and input applied voltage Fi is a function of time, output voltage across the capacitor E0, the current flowing through this circuit I, and we have two physical components, a resistance and the capacitor, and for these components we have well-defined mathematical relation between their input and output variable. For example, for a resistor, input variable is if IR, then output the voltage across the resistance is R times IR. Similarly, for a capacitor, the physical description of the capacitor is current through the capacitor is capacitance times the time derivative of voltage across the capacitor. So we apply KVL in this loop, and write the equation for this circuit. Sorry, we don't write the KVL equation. We just observe that the current through I is can be found by the potential difference across this resistance divided by the resistance value. So the input voltage EI, output voltage E naught. The current flow is input voltage minus E naught, potential difference across all divided by all. So here it is. IT is EIT minus E naught T divided by R. I have shown T here because these three signals are function of time. Then how to evaluate E naught T as a function of current? We will use the capacitor equation. For rearrange, we note that the capacitor voltage in here are the output voltage of the circuit, and if I rearrange dt here and 1 over c here, integrate on both sides, and I get E naught is derivative of IT divided by the capacitance. And these two equations can be changed to Laplace domain, and the current equation becomes IS is the Laplace transform of input voltage minus Laplace of output voltage divided by R. Similarly, the output voltage Laplace is Is divided by S times 1 over C. The integration process is replaced by 1 over S. And remember, we have these two equations in Laplace domain, and we have the corresponding block diagram, and I will explain it. Here is input voltage, output voltage. The difference between the two is coming here, EI minus E naught. Then it's being divided by the resistance value, 1 over R. So resistance is replaced by a block 1 over R. And after dividing, I get IFS. So this signal is the current. And that current, when divided by CFS, CS block gives E naught of it. And that's it. So this circuit is shown in this particular program. Is this representation is unique? No. We can have many different type of block diagram for the same circuit, and this is not a unique one. And next topic, or the main topic of our lecture, is rule or the block diagram reduction. We have a system that has many sub blocks, and we want to merge all of them into a single block diagram with input output relationship given as in the form of transfer function. And there are some rules. There are 8 rules. The number 1 rule is whenever we encounter two blocks that are connected in series, they can be simplified into a single block whose input-output relationship or the transfer function is G1 times G4, the product of the individual transfer functions. Then the rule 2 is we have two parallel blocks. Here if we see G2 and G3, they are parallel, being added together, and they can be replaced by a single block whose transfer function is the summation of individual blocks. Then we have a feedback loop. Here we have forward gain and feedback gain. It would be replaced by this particular thing, the forward gain over 1 minus forward gain times feedback gain. Here. Then there's rule 4, and rule 5 tell us about how to move the summing point ahead or behind a gain block. The rule 4 tells us if I have summing point behind a gain block, it can be shifted to ahead of the gain block in this way. That means this signal should be multiplied with G, and then it should enter the summing point. Now why is D here? It's because, for example, if this signal was A, this was B, and here was an output that would be A minus B, it's being multiplied with G, the output here would be A minus B times G. When I move this summing point ahead of the gain block, then this signal is AG. This signal becomes BG, and the output is AG minus BG. And if I did not multiply with G, then output would have been AG minus B. That would be wrong. And we change in such a way that these 3 points, either they are replaced or are shown in this way, or they are shown in this way. It doesn't affect rest of the block diagram. And then moving our summing point behind the block, and the incoming this signal should be multiplied with the block 1 over G, so that we can substitute these 3 points with an alternate block diagram. Then moving a branch point ahead of a block. Sorry, it's not an arrow. It's a branch point. This arrow is wrong. It shouldn't be here. And similarly, this arrow is wrong. It shouldn't be here. It's a block. I'm sorry. Then the moving a branch point behind a block. If I'm moving behind, it should be multiplied with the G. If there are two neighboring summing points, they can be slapped without affecting the overall block diagram. Now let's do an example, and we have this block diagram with the input signal and the output signal. In between there are a lot of things, a lot of blocks. There are 4 or 5 blocks and 3 summing points and a lot of signals. Now how do we simplify them? And the rule for simplification is we will be looking for the series connected blocks or parallel connected blocks, or in the loop back connection blocks. So here, if I see this, it seems to be a loop back, but it's not a loop back connection because we are taking a signal of A. This also is a loop back system, but it has an interference from outside, so it's not a standalone loop back. We cannot simplify it. Similarly, for the outer loop, we cannot simplify. So it seems this block diagram cannot be simplified, but we can do it if I move around the signal. For example, if I move this branch point ahead or move this summing point behind this G1 block, I will have some freedom. Or let's move this summing point behind G1 here, and you will notice that H2 has been changed and it should be divided by G1. Why? Because previously the signal was entering here, but now it is entering here. So this signal would be multiplied by G1. When it comes here, this part of the signal would have been multiplied by G of G1. That wasn't the case with the original block diagram. So the original signal that was coming should have been divided by G1 first, so that here the signal is not changed. And if we see here, what have we achieved? We have freed G1 and G2. This is a series connection. This can be reduced into G1, G2. Then we've got to see how do we change it further. And if we say that these summing points can be interchanged, if this summing point moves here and this comes here, we will have a simple feedback loop. This one. So this is our feedback loop, and this can be solved. We can replace it with a single block. How? The forward gain divided by 1 is plus minus. In denominator 1 minus h1 times g1 g2. This is comes from the rule number 3. We apply rule number 3 and we simplify the block. The further simplification is these two blocks are now in series. So G3 can be multiplied here. See here, G3 is. And now we have a simple feedback. Apply the rule 3 here. Again, we are having a feedback loop. So it can again be simplified using rule 3, and hence it is the reduced log line. And in by the what we mean by the block diagram reduction is we have multiple blocks, multiple signals, and we compress them into a single block. Given a relation between the input R and the output C, sorry, this should have been C, and then the block diagram reduction is often simpler than algebraic method. And in an alternate way, we could have assigned the signal names to all the errors, and from their mathematical relations, try to drive the relation between output and output. But the block diagram reduction, if we stick to our rules, it's simpler, it guides better towards solution. But obviously, sometimes the algebraic method is more powerful. And there is an homework exercise, and there are the A series are the solved N chapter problems, B series are the unsolved problems, and these are the ones that are related to the block diagram reduction. And this assignment is due on September 17th September 2018, and there are some instructions as well. And thank you for being here. Jazakallah. See you in next lecture.